Hello, everyone. Welcome to our second design review for the day, part of the version 14.3 sequence. And this is about discrete computation. I see a bunch of geometry here. Let's just get a sense of what we're going to see here. We've got geometry. That's the primary. Oh gosh, then quite separate thing. Oh my gosh. Oh, we got hyperbolic embedding. Is that actually working?
Somehow, yes.
What do you mean by somehow? Is it working or is it, I just want to see something exciting just for a second because I've been waiting for this for a while. And then we're going to come to the other things. But if I say carry tree of 100, for example, and then I say, I wish it didn't do that. Is there any way to stop it doing that?
No, it's actually the same underlying issue with the hyperbolic embedding is that we find a local minima instead of a global one. So,
So I just say hyperbolic embedding.
yes.
And is that the same issue, or is that's because I went to if I go to something like 1023, boy, it's taking its time. What's it doing?
Right. So that's the thing is, we are using the slow version of the spring embedding.
I'm sorry, but that doesn't look right. I mean, this
Right.
should be a uniform Poincare disk.
A uniform point, you mean the borders, the vertex uniformly distributed?
Yeah, I would think that that should be around. I mean, it's a we know what typical pictures of the Poincare disk look like for a tree. They're
Right.
equally distributed around the circumference.
Yes, so this one is a specific one, which is the spring embedding. So we use the spring force to actually, aggregate the vertices. So that's the key
In
thing.
hyperbolic space, or what?
Yes, in hyperbolic space.
Well, okay, we're going to come to this. I thought I was going to get really excited about this. I'm not as excited about this because this doesn't do what I wanted it to do. But okay, let's begin at the beginning then. Okay, find a minimum arc length curve or region. What? Find shortest curve is like in a region.
In a region, not of a region.
Right. So it's a
In a
find
region.
shortest path
Okay,
on
in a
the
region.
region.
In a region. Yes.
So I see. So this is a good example. Why the heck is it returning?
The B-spline curve is the best representation we can have approximately.
Okay, but so if I were to give this, if I give this, so if I why don't we have a print form for B-spline curve that looks nicer than this? We probably should have. We should probably have a summary box, right?
Yes, we'll work on that.
Okay. Um, but then what this is saying is within that region, which is a sphere. So if I were to do the following, if I were to say ball here,
That would be
a
just a
straight
straight.
line, right? Beautiful. Okay. And if I were to, I mean, let's say I have a, a I mean, so let's say I want to have a saddle surface or something here. How would I get that? How would I specify that? See what I'm asking? Let's
Um,
say I have a surface represented by, look, let's say I want
in the
plot 3D.
parametric region.
Okay, so let me do something like this. So what the hell?
That's a front-end bug,
Yes.
temporary in
Yeah,
prototype.
right. Okay, so I want to find the shortest path from here to there, for example.
Mhm.
Okay, so how would I do that?
Well, you could represent that using a parametric region, pretty much with the
So,
same,
I basically just say parametric region of that.
yeah.
No. Well, in this case, it's an implicit representation, right?
What?
Just tell me what to type.
No, I think it's just it's just that you need to put all the iterators in a list. Syntax error.
No. You need the XYZ for the parametric region, right? The parameterization there. Right?
Oh, I see what you're saying. Yes, that too. But you need to put the iterators in a list, don't you?
Why?
I don't know. Yeah, look at that.
So this case, we
Okay,
don't yet.
but by the way, I just want to comment that you should make better messaging for the case where those aren't on a list. Do you see what I'm saying?
Yes.
Okay, now if I say find shortest curve,
You need to find 2 points on it.
So
so I'm going to take this object, and then I'm going to say, well, let's see, if I say, oh gosh, I have to work this out. I want to say, I want to do the corners. So I want to do -2, -2, and then I need the value of that quantity, x squared minus y squared. I think I can work that out that it's 0, right? And then I want 2, 2, 0. Okay, so let's say I say graphics 3D, that, oh, ouch, ouch, ouch. And then I say show that with %30. Where's the line? I'd say graphics 3D %34. Well, that's pretty weird. I don't understand why it goes from 0 to 0.005. There isn't a line, is there? Is there a line that goes flat like that? I don't know.
can you actually in the last graphic put maybe draw the line with a red color? Just
Oh. Oh, it's %30. Ah, Hunkadorasaurus. So if I go 2 minus 2, Oh, for God's sake. Lovely. Well, that's magnificent. Might even be correct. Should be a hyperbola, shouldn't it?
Yeah.
Great. Now we just need some general relativistic spacetimes in here, which we should be able to get. I mean, I don't see any reason we shouldn't have those as parametric regions. This will work in any number of dimensions, right?
Does it show? I mean, up to 3, I
no.
know, but I think 3.
3.
We don't have meshes in higher dimensions.
Well, it depends. So in the case of a parametric region, we actually try to compute it more explicitly from the differential equations, so we can probably go higher dimensions.
I see.
I think we should seriously consider having some of the obvious metrics in here. I mean, there are a limited number of them. But maybe we need, just like we have coordinate system data, we might need some version of that. Does that make sense? Presumably, how does this interoperate with coordinate system data?
Well, there's some. Go on, Charles.
But so right now the only case where we handle coordinate system data is on arc length when you have a parametric representation.
Right, that's what I was thinking.
Right. So beside that, we don't have, and in general, for all the geometry, right, we are purely on the Euclidean space, so we don't have any metric or anything we carry.
Well, except there is a metric on these surfaces, right? You've got the thing you're computing is exactly equivalent. I guess I'm confused here. I mean, you can compute as you're about to compute the Gaussian curvature of the surface, right?
Yes. But like in our geometry, everything has an embedding space. Is it? We
I
don't.
get that.
Okay.
I get that. But I mean, on the surface, I guess I'm confused here. Jose is always good at explaining this stuff to me. We might want to ask Jose to join us again here.
Yep, I'll get him.
Yeah, I did actually have an intensive discussion with Jose about that. And it's good that you joined. You will actually explain the key difference here, because we don't actually carry the white matrix.
Okay, fine. All right, shortest curve distance.
That's this distance of the thing you just got. Or length.
Region distance function. What is this? Represents the shortest curve distance function over. That can't be right. It must be region, because we've already got a region distance construct, right?
It's just reusing it for another purpose.
Oh, I see. Oh, it's an update. Okay, I get it.
Yeah.
Right. Instead of introducing a new region shortest distance function, we can reuse that one.
Why are these just WFRs here?
Right. So, I mean, the geodesic curve, right, have a different specification and it get more complex to compute. Right. So right now we just decided to introduce them as WFR, especially for the plot, because we do an approximations.
Also, they're not.
Can I see those WFRs? Are they in the system yet?
No.
Okay. Can you send me something? Can you send me a?
I can
file?
send you
Just send me an email.
Right.
What is the difference between a shortest curve and a geodesic curve? Is the geodesic the extremum and the shortest is actually the shortest?
Yeah, the shortest is actually the shortest, where the geodesic is locally shortest.
I see. But so,
And
I don't
also,
understand why
it
we're not.
seemed to me
Yeah.
that geodesic is only really defined like for a surface in 3D.
Why? I mean,
Is
geodesic, I've certainly used geodesics in millions of different cases.
Yeah, but usually is on the hypersurface, right? N minus
Right.
one dimension.
Right. So yeah, it could be n-1 and n.
Right.
Well, okay, I'm more used to the actual space being.
The case for the geodesic, since you specify the point and probably a direction, so you want to actually wind up and know the whole length, and it gets a little bit more convoluted and complicated. So right now, it's kind of more a lightweight version, where you have to specify the length of that geodesics specifications.
Well, there's no, where is it? Point.
The point, A is the direction or the angle, theta.
What's R?
R is kind of that length. Right now,
Oh, I see. So you're saying this is like, in the case of geo, this is like, what is it called? Geo direction. Hi there. This way of specifying a geodesic, what is the thing where you have a bearing, when you have a geo thing where you have an anchor point and a bearing? What's that called?
Yes, I think you are thinking of geodisplacement.
Right.
It's
No,
geodestination, and you give a point and then a direction and a distance.
Right, which is the exact analog of this. So on a surface, I mean, there is something that's like that, right? So that would be geo displacement.
Yes, this takes a distance and a direction.
Okay, and there are multiple types of, okay, a distance and a direction.
And then you need geodestination to specify the initial point.
I see. So geodestination takes an initial point.
Yeah.
And then geodisplacement. I
Yes,
see. Then that's
or directly the pair. Yep.
Okay, so that's the direct analog of this function here. Point, and then it's R theta, basically. Correct?
Yeah.
Although it's unclear to me what the coordinate system for theta should be.
Right. In geo, it's a bearing angle, so clockwise from north.
But what is it in this case, Charles, for the geodesic curve, for example? When you specify geodesic curve, what are you specifying? This direction, you have some direction A. What is that direction A? Charles, I think you must be on mute or something.
Oh, sorry, I'm back. Yes, I was on mute. So essentially that direction represent the angle from
But is it a unit vector or what?
Yes, it's a unit vector, because from the differential equation, so it's the first derivative at that point, that direction.
Okay. So that's something we're not supporting in geo, but we probably could as a unit vector instead of the angle. Is that true?
We could. Yeah. I mean, we have geovector, which takes again a bearing angle to specify the direction.
I see. But geovector could also be a unit vector, probably. Northward, eastward displacement.
Yes.
Okay, but that's what this is doing relative to the XY coordinate system or whatever in geodesic curve. Is that correct, Charles?
Yes, it is. Sorry.
Okay, but to me, it seems like this should be geodesic destination, not geodesic curve.
But we get, I mean, what do you get out from geodisplacement?
Another point.
A
Right.
point. So this is
This is a whole curve.
right, but we might also want the function geodesic destination.
I see. Yes.
So in geo, the equivalent of the curve would be the geopath, which can also be specified as a pair, point, and displacement.
Okay, so if I say geopath, what does it take? You know, this stupid thing with this better get fixed for version 14.3. This thing here.
Yeah, in geopath, that would be the third one. So the location, the distance, and the angle.
Okay, but if I say here London, New York, okay, that just remains a geopath like that. And if I say geographics,
right, then it resolves all the entities at the same time.
I hope we're going to fix this in 14.3. Tiles, are we?
Yes, it's going to get better. Yeah.
Good. Okay, so that's beautiful. So let's so what's the analog of all of that for our general? I mean, I hope we're going to get all these sphere functions. I know we're not going to get it immediately, but you know, sphere position, all this kind of stuff, sphere path, and so on. But this is the more general version of that, right, Roger and Charles?
Yes.
So we really, I mean, what happens here is pretty nice. And we could use that same idea.
So geodesics can be specified in two ways. This way in which you give 2 points, which in geo it's called the inverse way, and the direct way in which you give the initial point and a direction and a distance. So these are two alternative ways. It's like a shoot. How's it called? A shooting
It's a boundary
problem.
value problem or initial value problem.
Exactly.
Yeah.
Yep.
Yeah.
Mm-hmm.
Okay, but so we probably are going to want the same thing for geodesic curves. So find shortest curve is with respect to 2 points.
Yes.
Shortest curve distance with respect
But it also
to 2
works
points.
in you know, for any kind of region. Do you see what I'm saying?
It's not just on the surface or
Right. It's
Yeah, I get it. So if you have a Sierpinski, for example, it's threading through all those different pieces.
Yeah.
Which is very cool. But I'm a little bit confused now. Okay, so the parametric surface, it represents the surface. So what I was raising, Jose, earlier was the analogy between this and coordinate systems and metrics in general relativity.
Mm-hmm.
And I understand that the metric here, I mean, I've been through this confusion at least 5 times in my life. There is an intrinsic metric inside in the surface, right? Different from the embedding space. Can you explain?
Exactly.
Yeah. So walk me through how that works and how we should think about it here.
So we have an ambient space which has a metric, which in this case is the Euclidean metric.
Mm-hmm.
And then we have a surface on that embedded there. And that surface can be thought of in 2 different ways, as something embedded in the external and ambient space or as something intrinsic.
Yep.
And so the key point there is looking at the curvature. The curvature is something that has 2 parts, the intrinsic part and the extrinsic part. The intrinsic part depends only on the intrinsic metric. It's something purely intrinsic. And so when people discovered from Gauss the new geometries, was just the realization that one can focus on these intrinsic spaces and completely forget about embedding the ambient space, etc. And for many problems, that's all you want.
So in our world, where we have parametric surfaces,
Mhm.
The intrinsic metric is with respect to the parameters that define the parametric surface. Is that true?
Yes. So once you have the ambient metric and the surface parameterized, for example, you can compute what's the intrinsic metric induced by the ambient metric. And once you have that intrinsic metric, you can just forget about the ambient metric or where it came from.
Right, but that's then with respect to parametric the parametric coordinates in the surface, correct? So it's u and v. I mean, in the surface there's an x, y, and z from the ambient space,
Yes.
and then there's a u and v, which are the parametric coordinates intrinsic to the surface. Is that right?
Yes, but of course, in order to induce the metric, you need to know the relation between them, right? So it's a two-dimensional surface, so it's going to have, of course, two coordinates.
Yes.
But in order to induce the metric, you need to know the relation. Once you know the two-dimensional metric induced, then you can compute the extrinsic curvature and all the extrinsic properties. So sorry, all the intrinsic properties. Intrinsic properties.
So
exactly.
for a sphere, for example, where we have, I mean, we've got lat long coordinates, and we can compute, areas on the sphere relative to those coordinates.
Right, because we know, or we can compute the metric in terms of those coordinates. Yes, the intrinsic metric. Yep.
Okay, so if we have a parametric surface like what I set up wherever it was here, right? These are extrinsic coordinates, but we could parameterize this surface in terms of coordinates u and v intrinsic to the surface.
Well, the extrinsic coordinates, I would say, are the A, B, and C represented by the parametric region. Those are the Euclidean, right?
I see.
And so,
yeah, okay.
Now the X and Y are the coordinates on the surface. And because we know the relation between A, B, C, and X, Y, then we can like pull back the metric, the ambient metric into the surface.
Okay. All right. So I'm still trying to understand. Find shortest curve. The curve is quoted in the coordinate system, in the ambient coordinate system. How would we get coordinates? I mean, given a parametric region, we could imagine getting coordinates inside the surface, correct? And we could imagine, giving that line with respect to coordinates intrinsic to the surface.
Right. If this gave a curve x of t, y of t, we could use this formula xy x squared minus y squared to get the ambient coordinates.
Okay.
It's totally fine to give this representation. This representation is better to draw it in 3 dimensions.
Yeah. I understand. Okay. Charles and Roger, does this all make sense to you, or are you wondering? I mean, we just need correspondence between the geo stuff and the geodesic stuff, so to speak.
I mean, the geo stuff, we do have a correspondence that we did many versions ago. But you was talking more specifically for the things we're talking about today, right? The geo. Okay.
Yeah, I'm asking, if I say,
but I think that supporting, like the 2-point version for the geodesic curve, as opposed to initial and direction, I think we can do that.
But I think at the end of the conversation, right, it's a matter of representation, right? So that's why then I tend to split the geodesic curve differently, because you don't have a unique representation, and you want to use that intrinsic representation to do the computation you want in this case, right? The U and V from that surface, right? And is what we don't provide in this case. We just provide the representation in, in Rn, or in the ambient space where we are. right? And that
Yes.
was even a reason why we split the shortest curve, because that one it's fine because you're in the ambient space, where the geodesic, you want that intrinsic representation, right? And we needed to do that conversion. We haven't done, right? And in some cases, people want the geodesic curve with that unit length, right? So
No, I agree. I agree.
You have that.
Just like in the geo case, where we have,
right,
geovector and geodestination and so on.
Right.
But so I'm still confused by something. In the geo case, we have these geogrid coordinates, which are, let's see, we have lat long, and then we have geogrid coordinates. Can you help me out with what? How do those correspond to the ambient space versus the intrinsic coordinates here?
So there we have mappings. So in general, we could say that when we have a curved surface, we can construct little patches around it, which are going to be close to it. So the coordinates on those patches are more or less arbitrary. And so we can use various types of coordinates that are convenient for one reason or the other. And those correspond to the grid coordinates. Lat long are grid coordinates too, in the projection that we call equirectangular.
I see.
Right? So any choice of two coordinates on the sphere, we can say it's a projection.
Right.
The only thing we require is that they keep orientation, that countries do not look.
But you also have X, Y, Z. Those are truly the ambient space coordinates.
Exactly.
That's
exactly.
Right.
Yep. So this line with triples, we might think of them as XYZs, geoposition XYZ.
Right. But we might also want a projection version with respect to, so a projection we can think of as being some coordinate system on the surface, so to speak, which will be two coordinates in this case of a two-dimensional surface in 3D space.
Right. Depending on what the surface is, whether it is a torus or it is a cylinder or whatever, it may be more convenient to choose one or the other. But any choice of two coordinates is like a projection, yes.
Right, but there may be multiple charts and all kinds of weird stuff in the projected case. Is that true? Or can we always have?
Yes. If the, for example, because the Earth is a sphere, it's a closed surface, we cannot use a single coordinate system to do everything continuously. So we will have to cut it somewhere.
Right.
So at least
conveniently in Antarctica.
Our geometry is sort of global, right? And it's very hard to do global geometry in general with charts and everything.
I guess, but so what we could imagine here, what we're doing is this is all coordinates in the ambient space, except for what you currently have as geodesic curve, which is coordinates on the surface. Correct? Because the R that you have in the geodesic curve specification is an R in the surface. It's a certain distance in the surface, correct?
Correct. Is actually that arc length of the geodesic, yes.
Right.
But you could also, it's simplified, so there's literally a differential equation that defines how to do it locally.
Yeah.
And it's not guaranteed to be minimal, right? Or shortest. And it's literally only defined for hypersurfaces.
Okay, hold on. Let's just walk through this again, okay? So find shortest curve operates in a space with some ambient coordinate system and returns a result that is a representation of that curve. I mean, there are fairly few other functions that return geometric objects like this. Is that a true statement? I mean, that return.
No,
all the geometry return.
Yeah.
Okay.
But you do intersection, region intersection is
returns a region. It's just I'm not used to seeing it return just a plain line. But
that is a region.
No, I get it. Okay. There's an argument for a case like this. We might want a better print form, but that's a different.
Yes.
And certainly for the B-spline case, we definitely want a better print form.
I mean, we did introduce the primitives are a little bit tricky, but we did introduce better print forms for polygon and polyhedron because they're typically massively big.
Yes.
But we haven't gone back and done that for others.
The line and so on.
Right.
It's a little weird that find shortest curve, I assume it has a default working precision. That in principle, in some, there presumably is a parametric line that you could give. In fact, it is a parametric region that just has, this is where I'm getting confused, because a parametric line would again have 3 coordinates there.
Mhm.
Right? You could write a parametric line as, this would be something like the following. You could say parametric region of, x, y, f of x, y. No, not x, y. I would say, x of t, y of t.
Exactly. And z of t.
Right. And then t goes from whatever it is.
Right.
Okay, so in principle, find shortest curve could return a parametric region.
Yes, but we can't. But we wouldn't solve very many cases if we did that.
No, I get it. But so in principle, just in terms of the design, find shortest curve should have a default working precision. And should just, which it should default to machine precision. It just does what it does.
Right. So yes, we have working precision. So, and it depends on the type of input, right? So essentially what happens is when we have a parametric region and which not any arbitrary parametric region, but for a specific case where the surface, the corresponding is C2 continuous, right?
Mm-hmm.
We can actually solve the differential equation correctly, and then we return you actually that a corresponding parametric region. We describe the actual line, the shortest
in what
part.
case can you do that?
In the parametric region, that's why that case is missed. Normally for parametric region, like if you take a sphere, for example, we can actually explicitly do that and return you a parametric region. And I thought that it was implemented, or it should be in the documentation, right? And in the case where we cannot actually solve the differential equation correctly, so we fall back into the approximative method.
That's a case where you've got an exact thing.
Right. If you look,
God, I hate it when you do this. I hate it when you define these things and then use them. You should really put them all in one function here.
Yes, we are working on that.
Okay,
we'll fix that. Should be cleaner. So if you go on scope, hopefully it's written there. That's method. And the formula region. So I think if you evaluate the parametric case above, it should return you.
Which case?
So if you go back above the formula region section, and the last example.
This one here.
Yes. And if you remove the semicolon at the end of the shortest curve.
Hate it. No. That's still just an approximate line.
I think so maybe when we said working precision, the convention we've had, I think working precision infinity forces it to try really hard.
Well, let's try.
It's probably the build. The build may be old or something. I think normally should. No, I think this is
okay, fine.
Yep.
But S&T are real points, right? So shouldn't this fall back to?
Oh yeah.
Oh shit, yeah.
No, even in that case, I think it So it should actually return a parametric region. I think it's just this build.
This is such a trap. Please don't do this, of doing these things where you define silly one-letter variables. Please don't do that.
Yes,
just like
the final version won't have that. We'll fix that.
Okay, all right.
I mean, what we don't want is really big inputs.
No, I
like-
agree with you. I agree.
Okay.
I agree.
Yeah. You have to
What
remove the
happened there?
T.
Oh, okay.
Yeah, it's
just not here in this build. Okay.
yes, but
All right, fine.
But like the case of a sphere, normally we should be able to return you the parametric formula. Unfortunately, inside you have the interpolating function, which is solution, but
okay. So let's just understand. You know, we've got find shortest curve. It's a find function. So it's a you know, so we expect a bit of findery, like machine precision numbers and so on.
Yep. And it's truly necessary. I mean, for the level of generality that we're trying.
I'm sure it is. I'm sure it is. I don't think it's super necessary to have. I'm just trying to understand what's going on. Okay. So the thing you're calling geodesic curve, I'm confused. I mean, you could also have a find geodesic curve, correct? Which will be different from find shortest curve in general.
Yes. And that was the reason why we decided to put it first in the repository, because of that parameter R on the additional computation to actually return you the form someone will expect. Like in your case, you expect that you'll get a parametric region where if it's a curve, is parameterized by T from 0 to the arc length of your full geodesic if it self-intersects. So the output should satisfy a certain set of criteria. Right now, we don't provide. We don't want to return a line or a B-spline curve for a geodesic curve.
Sorry, I got distracted for a second. Could you say that again, please?
So I mean that, so in the case of a geodesic curve, for example, on a sphere or on a torus, right, you expect that the output will be a parametric region, which is, you know, parameterized by T.
Yep.
In this case, and from 0 to the arc length of your geodesic, if it's in a closed surface or even in a surface with boundary, right?
Yeah.
So it's what, you know, we don't need in find shortest curve, but we need for geodesic, and we haven't yet implemented. And so that was one of the reasons why we decided to push it as a function repository for the time being.
Okay.
And see if people are interested, then we can do that additional work on top.
Okay, but I think the design, though, I mean, why is a geodesic curve? So it's less findy because it is just this local differential equation that you're following, correct? It's not a find-like thing. It's just you solve the differential equation, you have it.
Yes, actually, right.
Whereas find shortest curve, it can flap around and you know, like there might be 3 identical shortest curves and it's going to find one of them, right?
Yes.
I'm thinking that for find geodesic, you know, if you have if you have a boundary value problem, there can be multiple solutions to that too.
Exactly. Whereas there's not, in the case of, look, find shortest curve is one thing where you're given the boundary points. And that is the analog. I'm sorry, what's the geo analog? That's geopath, right? Geopath
is the curve.
It's the curve.
Right? So find shortest curve is a reasonable name for something with 2 endpoints.
But imagine that you're at antipodal points on the
No,
sphere.
I know. You're only finding one of them. Find shortest curve finds a curve that is a shortest curve between those 2 points.
Right.
That's what I'm understanding. Is that right?
Yes, you find A. Yep.
Right. Okay. So fine. So it's correctly named in my view. Okay. The next issue is the analog of geovector, which is start at a point, go a certain distance in a specified direction. That's unique. And that's what you're calling geodesic curve here, right?
Yes, if that's analog, yes. Remove.
Well, so I think it would be nice, what is the, let's see, when you say geovector, it's because a straight line, go ahead, what were you going to say?
I think you are mixing geovector and geodisplacement. Geovector is the tangent thing, the little vector at a point. Geodisplacement is the thing that takes an arbitrary distance and an arbitrary angle.
Okay. So this will be geodesic displacement then. This thing, geodesic displacement will take you to the end point. It doesn't take you along the path.
Exactly.
Now, this geovector thing is a tangent vector, right?
Yes, geovector is something that we would use for, I don't know, the magnetic field at a given point.
Right, but why don't we have a thing called tangent vector of a region at a point? Is that silly?
Well, it's similar, like we have normal vector, we just never needed it.
Yeah.
We have normal vector to a region, right?
No, I mean, we have the option, right? But we don't really have a function. We compute it explicitly.
What do you mean we have an option?
The main case where we use normal vectors is for rendering.
Yeah, I know.
For light computation.
But let's say I wanted to compute I mean, look, in this case, there's a tangent vector field here, and there's a normal vector field, right, for that surface. Right?
Yes. I mean, there are different numbers of them.
No, I understand. But at a given point, there is a tangent vector.
Vectors, yeah. That's a 2D.
Yeah, okay. There's two orthogonal, in this case, tangent vectors. There's a tangent space.
Yeah.
And so why do we not need stuff like that? Or do we?
I mean, right now, most of the geometry functionality avoid to go to the differential geometry, right? With tangent vector and chart.
Yes.
Right.
Yeah,
and carry all that. So
we don't need it because we have like directional derivatives where you can compute. Well, I'm still a little confused because when you have these numerical surfaces, basically, you can imagine numerical tangent vectors. And most of the time, we've got a symbolic form and we're computing directional derivatives and things. Is that right? Or am I confused?
I mean, the use cases that we've had for geometry is, global geometry. Like we understand the whole thing. We want to solve something over it. We want to plot something over it. We want to create the shape. It's just not the main use case. Hasn't been.
But I mean, usually those are additional information like you highlighted, a specific matrix you want to attach to your region, your geometry, right? We didn't need it because we live in the Euclidean space. Right?
Sorry, say that again. I got distracted again. Say it again. What?
I mean, most of the geometry live purely in the Euclidean space, so we don't need to have additional local information.
Yes, I get it.
Right. So
but we're trying to live now intrinsically in the surface with, for example, Gaussian curvature being computed. Right, because that's an intrinsic feature of the surface.
Yes. But you see, you can do without having to describe the local topology, right?
Let me just look at region Gaussian curvature.
So in general, curvature is this Riemann thing, right? It's a tensor. And what you are doing here is using a bunch of scalars to define, to describe the main properties of that tensor.
I'm very confused by this. I thought, oh boy, why isn't there a local version of this? I don't understand. Why is there just a single? I mean, it's constant on a sphere, but why? If I were to pick some other kind of thing here, other than a sphere, like an ellipsoid, for example, we have ellipsoid, don't we?
Yeah.
And let's say I say AB. Ooh, what do I need to give here?
It's a center
Wait.
and radii, you know. And if you want the axis aligned, probably need to give 3 of those. A, B, C.
Yeah, okay.
Yeah.
Is that, I'm sorry, I just don't know. Is the Gaussian curvature is constant over the surface of an ellipsoid, or what?
This is presumably computed at the point 1, 0, 0?
At that point, yeah.
Oh, I see. Oh, that's why I was confused. Okay, so that's the Gaussian curvature at a point. So if I do that, Coolosaurus. Okay, so if I now ask for mean curvature, so how do I get the coordinates of the pieces of the tensor, the Ricci tensor, for example? Does that not make any sense?
Well,
if I can do these things, I should be able to get metrics and things, right?
This is something computed from the metric. So the metric is intrinsically there. And so from the metric, you compute the curvature, which in general, it will be a rank 4 tensor. But for the case of two-dimensional surfaces, that tensor only contains a number, which is the Gaussian curvature.
Or these other curvature quantities, which are different pieces of in this case, there's only one independent component.
Remember the discussion before in which we were separating the intrinsic and the extrinsic curvature.
Mm-hmm.
So the intrinsic curvature in this case is just one number, the Gaussian curvature.
Yes.
That's the case for all two-dimensional surfaces.
Yep.
The extrinsic curvature has other numbers. And that's when we have to worry about mean curvature, max curvature.
Okay, fine. But so now if I go to, we don't yet support higher dimensional geometry, true or not true? I mean, we have higher dimensional polytopes, don't we?
No. But we have a bunch of high dimensional geometry, but they're usually simpler regions. They're not like really complicated. They're like piecewise linear, like an affine space. Yeah, ball is fine in any dimension.
Right. So if I do volume of that, I'll get pi cubed, pi squared, whatever it is.
Yeah. Well,
it's
region measure.
Okay. So now if I say region Gaussian curvature of ball of 4, X, Y, Z, W.
No. So right now we just support curvature on the surface.
That's the traditional concept of Gaussian curvature.
Yes. There are several extensions, right? But it's, yeah, like you say, it's a traditional version.
Okay, but if we were to go to higher dimensions, then we would start having to get curvature tensors, yes?
The generalization of the Gaussian curvature is the Ricci scalar in higher dimension, which is still a scalar. But now that scalar doesn't exhaust all the intrinsic curvature. You need more.
Yes.
That's why you need Ricci and other things.
Right. Which we should in principle be able to compute. But not yet. We don't have a reason to compute that yet because we're not dealing with, you know, three-dimensional things embedded in 4 dimensions or whatever else. Is that right?
Yes. There is also the problem of how to express it, because in order to express those tensors, we would have to make coordinate choices.
Yeah,
That's a nice thing of scalars. You don't need to do that.
Indeed. All right. So these functions, I think I understand.
Gotta go.
Okay. All right. Let's continue just a little bit here. So I think I understand these functions. Region curvature function. What is that? Which
Right.
curvature?
Oops. No, so it's similar to the region distance function, but for faster computation, right? So essentially, you can give the region as well as just the region, and then we pre-compute the curvature. So if you want to
Okay. So I get it. So this here, I can just do this.
Yep. Not yet working, but yes.
Okay, I understand. But that's going to return
A region curvature function. Yep.
Fair enough. Okay. So again, back to this. What I think we're concluding is that this, I mean, we really want to talk about this as somehow we've got to indicate this is a local object, not a curve. By curve, we're going to say the two ends of the curve type thing. Rather, this is a geodesic, direction or something. It's not really a direction. It's a geodesic, and we're calling it in the geo case, displacement is where you get to. Is that correct?
No, that's destination. Displacement is these pair of numbers, direction, distance.
The endpoint.
Yeah, okay, fine. But so we need an analog of that. If this is going to be a whole curve. It's kind of a geodesic curve in a certain direction starting at a certain point. It's kind of like almost an anchored, what do we want to call it? I mean, it's not a very good name, but something which geodesic distance curve. That's a lousy, stupid name. It's kind of like you're going along a radius vector. I mean, a rather stupid name would be. That would be like geovector. It's not a good name. We need some name like this. I don't know what it is. Right, to indicate that this is again, the closest analogy in geo is geodisplacement, which goes to the two endpoints, right? But not the curve in between.
But geodisplacement is the pair of distance angle. It doesn't know where it started and it doesn't know where it will end. That's the role of geodestination.
I see.
So it's like that's why we called it displacement.
Okay, so we could have a geodesic destination that takes a starting point and a geodesic displacement.
For example, and it would give another point.
Yeah. And what would the displacement have in it in the geodesic case? Just an angle.
I would say a distance and an angle.
The length of the geodesic and the angle.
Yep. I mean,
or a unit vector.
It's an angle because it's 2D. if this was working in higher dimension, it would have to be some sort of exact
unit vector
direction, length and unit vector.
right. So, and that would return a point. But now we could also imagine returning a path here.
Right.
So it's almost like,
I was trying to find a name like integrate geodesic, something like that, because this is just sending the information to and dissolve and integrating there.
okay. But geodesic path, sorry, once again, geopath
Mhm.
is something it doesn't evaluate, right? It's just this.
Right. But that's more like an efficiency thing because we don't want all these things to evaluate separately.
Right. But we could have a geodesic path which does evaluate.
Right.
You know, a B-spline or whatever the heck it is. So I think that's the analog, isn't it? Geodesic path is what we want, not geodesic curve. I think. No, but that's wrong again, because path here gives us the path from a starting point to an ending point. Is there a way of doing geopath with a displacement?
Yes. So what you had just you can say list point and then comma geodisplacement, or you can put directly the distance and the angle.
So this thing here is very similar to find shortest curve. Geodesic path but we can't call it find shortest path because we have a different meaning for find shortest path. So that would otherwise be called find geodesic path, right? Except it might, no, we want shortest rather than geodesic, which is just extremal. Okay, so what we want here, the alternative would be geodesic path of geodesic displacement. No, what the heck is it? It's a starting point and a geodisplacement. Yes, geodesic displacement.
Right. That's what geopath does. Yeah. You can actually put a bunch of geodisplacements and it will just jump from one to another.
PT1 and then we have a geodesic displacement. My conclusion is this needs more design and that even the WFR function should have a more encrusted name. Charles.
Yes, I agree. But my question in terms of going to geodesic displacement, which is all good and nice for geo, right? But in the workflow for geometry, right, those displacement is not a concept which will be used anywhere else.
Why not?
Because usually we don't have that action of displacing a point, right? You are at a point, you operate at a point, usually in geometry. We could, but I just don't see why that will be useful. Right? And introducing it just for this geodesic, I don't think that would be that great.
It's true that displacement is a word that we introduced. Remember, Stephen, that we were thinking of something called geocourse? Because we were thinking of the navigation.
Yep. Well, okay. So look, I'd like to understand the geometry workflow here. What is the geometry workflow that you see for this?
It's, at least from my perspective, the geometry workflow usually about the output than the input. Right? So usually the type of output somebody wants and you should be able to manipulate or get result out of it, out of the geodesic, than actually how you specify to get it, right? And usually it's the region, the point, and the direction.
And then what do you want out? Do you want the curve or do you want the destination point?
Usually you want the curve.
And what are you going to do with the curve?
Any type of operation, since it's a curve, so you have a parameterization, you can compute the arc length, the way the curve is specified. That's why before I was saying, if we return it as a parametric region with one argument.
Okay, we got two cases here, which in GeoPath we are dealing with by 0.1, 0.2, or 0.1 geodisplacement, right?
Right.
Yep.
That's how we're handling the two different versions of how to specify a path. So find shortest curve. Presumably it takes a list of points. Is that correct? What does it do right now?
So find shortest curve just take 2 points, the starting and the end point.
Yeah, I don't think it's right. I mean, so that's find shortest path, again, takes 2 points, right?
Yes.
Doesn't take a list.
The same for
Right,
no,
but then find shortest curve. Yeah, the thing is, as you say, it's not. Damn. You see, the problem is that, look, it would be, find shortest path looks like that. So that's what it is, basically, right?
yes.
What about something like directional curve? Oh no, there's another thing here. We need to give the radius.
Right.
I hate the fact that, I mean, it isn't really a fine directional curve anymore, is it? Because it's just, you just get it.
Yes, it's fully specified.
I don't like geodesic because when I think of geodesics, I think of their endpoints. And I think of the shortest path between their endpoints. Although I have to admit that I've used geodesic balls a lot, where it's a center point and it's a certain distance. I mean, for me, so let's look at that point that we might say geodesic ball, region, point, radius. That's the thing to define.
In a sense, if the other one was the find shortest curve, this is the find straightest curve you want.
But there's no find in it.
Right. But I'm trying to look for the analogy with the other one. So in the other one, it was a matter of distance. Here, it's a matter of keeping being as straight as you can in that region. That's the geodesic condition, the differential geodesic condition.
Well, but you can also argue that we say shortest because you're in the Euclidean, which is the straightest, right? So those two terms usually interchange.
Yes, but in the other one, it was, as Roger was saying, a boundary value problem, right? Like a variational problem, distance. Here, it's the idea of keep moving as straight as you can with the direction you started. I mean, you don't know whether it's going to be shortest or not. You may be on the sphere and come back to the same position you started.
Yeah. All right, this requires more work. We've got some stuff here that we understand clearly, and we've got some other stuff we do not understand yet. So just come up with a more encrusted name for the WFR. Fair?
Yes, that's good.
And then please let's not forget this discussion because we're going to have to resolve this. I do think geodesic ball is not a crazy thing to have. I mean, having the volume of the geodesic ball is useful. Does that make sense?
What's
So-
the geodesic ball?
Start at a point P and go a distance R, and you
Oh,
see
the
what you
curve.
have.
Okay, I see. Okay.
It's like a sphere. It's a generalized ball,
Oh, okay.
right? So you can ask for the volume of the geodesic ball, for example.
In
So, for
geo, that's the
example,
geodisk.
yes, right.
I see.
So it's the analog of geodisk. I mean, I think that would be a cool thing to have. You can ask then on a sphere, you can ask the geodesic ball, and we'll give you, you know, the area of the cap, so to speak. See what I'm saying?
Mhm. Yep.
I don't think that should be that hard to compute. It seems like a slam dunk thing to have. I certainly know I've used it a bunch. Okay, but we haven't solved the problem of we've got find shortest curve. Now we want to specify. I mean, I think that geodesic directional curve is a good encrusted name for this thing. Does that make sense, or is that?
The name makes perfect sense to me. It's a bit long, but it's very
that's okay
precise.
yeah.
It's very precise.
It have all the information, I guess.
Okay, so maybe that's what the WFR should be called. What does geodesic plot do?
Oh, it was just a visualization of it. So
Okay,
if you
so
just
fine, that's fine.
right, I think.
I mean, that's a typical WFR thing. Okay. What's human motion? Is that a thing in the parameter space, in the pose parameter space or something?
Yes, we are just trying to build some example based on that. So people use the geodesic to do human motion and such.
That's also relevant to robots, isn't it?
Yes.
That's cool. Okay, a lot of wonderful stuff. All right, so we'll continue at another time. And I can see meshes coming up. Is that really going to finally be able to repair meshes?
Part of it's hard to repair everything, but yes.
I just have to believe that with modern machine learning, one can repair meshes. I find it impossible to believe that can't be done at this point.
I think it's possible, but you haven't yet explored that side. So this is essentially just for the processing. But
I see. Sander on our live stream is asking, can one make isodistance contours on a surface? Isodistance contours. Isodistance contours. So those are a set of lines. No, this doesn't immediately give you a way to do that, right? Because that's
probably if you look at, so we're introducing region value plot. And if you actually give it the shortest curve distance, it will actually build it with those contour.
I see what you're saying. Shortest curve distance from a given point, anchored at a point.
Yes.
Then it will make contours that are specified distances away from that point.
Yep.
I see. So from a point, you can make the ISO distance. Yes, I understand. I wonder if there's a desire to have something when we give the mesh, something we might think about as a named mesh. Right? I don't know whether we have named meshes. Do we have those yet?
So when you say name mesh, what do you mean?
I mean, mesh function goes to some named thing. So right now, mesh function, goes to
Right.
#1, #2 or something in the case of the surface, or I could say #3, and then it would, do the Z coordinate. But the question is, well, maybe the whole point is, no, the right answer is mesh function goes to shortest curve distance of, is that right? Does that do it? Yeah, I think that does it, doesn't it? If the shortest curve distance from a given anchor point to the position #1, #2, #3, I think we give the right thing, I think.
Yes, it's kind of similar even to the idea of how we build that region value function from the geodesic, yes. The mesh function.
All right, last thing from Sander here. Find shortest curves can handle periodic domains like a torus. So a parametric surface can have a cut. What about Mobius strips and so on? I think the issue is you have to be able to parameterize the surface. So if you have to have multiple coordinate charts, so be it. I mean, in other words, for a torus, for example, okay, first point is find shortest curve is going to find a shortest curve. So if you can go one way around the torus or one way around the sphere or another, it's just going to give you one of those. Right?
Right. Maybe it's highlighting the case where like the Klein border, where the surface is not orientable, right? So you can easily split in between.
Sure, but that's because you have to have two coordinate charts to cover the surface.
Exactly. Yep.
But if you are parameterizing it, you have to have two coordinate charts. If you didn't parameterize it, I think this will work just fine, won't it? There's no problem for find shortest curve on a Klein bottle. We'll happily just give you, if we had a specification of a Klein bottle, which I don't think we do, but for a torus, for example, it will happily just find the shortest curve. Right?
Yes.
It doesn't care that there's a coordinate, there's multiple coordinate charts.
Yep,
That's only relevant if you were parameterizing the surface. Correct?
Yes.
The Klein bottle is problematic when embedded in 3D, but it has no problem when embedded in 4D. It's a traditional example that sometimes you have to go higher in dimensions to embed things.
It's the Klein bottle, it's two-dimensional surface.
Yes.
What's the problem? I mean, if we had a specification of a Klein bottle, we can just find shortest curve happily there.
But in 3 dimensions, it's going to self-intersect. And so what device computing distances might get confused when it reaches one of these points of self-intersection.
Well, but this is the shortest part, right? We don't guarantee that you are working on the surface and avoiding.
Yeah, it doesn't. When the surface goes through and it maintains what you think of as one side of the surface and it self-intersects, at that cusp, so to speak, where they self-intersect, if the shortest curve jumps to the other side of the surface, so to speak, so be it.
Yep.
But we are computing curves on the surface, on the 2D surface, right? So it doesn't make sense to think about one side or the other side. Or are you thinking of the interior?
The point is that we're not distinguishing. It's not an oriented surface where we're saying we're only going to go on one side of this thing. In other words, like for a
Mhm.
sphere, we're not
Mhm.
distinguishing the exterior of the sphere and the inward pointing normals and the outward pointing normals.
Mhm. Yes.
So I think that point is, I mean, for what we're doing here, because we're not distinguishing those things, we're not sort of, it's like like some kind of closed interval type story of, do we distinguish the inward pointing normals and the outward pointing normals in the case of a sphere? I don't think we care. We're just distinguishing points on the surface.
Mhm.
Yes.
So I think that's okay. Sandra is asking, does it jump over the 2 pi 0 line, or is it all done numerically? Remember, in the embedding space, there's no jump. There is on the sphere, in the intrinsic coordinates of the sphere, there's a jump. But in the embedding space, the path just goes, some XYZ values to other ones, right? There is no discontinuity. I think I'm correct in saying that, right, guys?
Yes, there's no
Yes.
discontinuity.
All right. Good stuff. I can see we've got a bunch of juicy things. I'm looking forward to these. Oh boy. A lot of good stuff here. But it's going to take us a while. Oh, good. That's nice. Does that give us docking for molecules yet?
No. Docking is more complicated. I had a discussion with Bob about it. So we're exploring that side, but not yet.
Okay. Sounds good. All right. Thanks a lot. Thank you, folks.